Previously, we've looked at vector-valued functions which sweep out curves in R2 and R3. In this lecture, we're going to do a lot of calculus on vector-valued functions. It's going to feel like an entire semester of material in one lecture, but that's because calculus on vector-valued functions, or at least the notions that we're going to look at in this lecture, including limits, continuity, differentiability, and integrability, really follow directly from the ideas that you would have built up in single-variable calculus. Because if we're looking at a vector-valued function and we want to do something like analyze whether or not this function is differentiable, it amounts to asking the question 3 times for each of the component functions. So that's the take-home message of this lecture, is that if we want to do an action like integrate a vector-valued function, we're just going to do it component by component. And then each of these component functions is a scalar-valued single variable function, just like you've seen in Calc 1. So with that in mind, we're going to run through these topics fairly quickly. So this is just going to be an overview. We're not really going to dig into the notions of limit, continuity, differentiability, or integrability more than we do in this lecture for these vector value functions. So let's start with limit. Taking a limit, of course, is the underwriting notion behind all of the other topics I mentioned. So we can't discuss continuity, differentiability, or integrability if we don't have the notion of a limit. So what do we mean when we take the limit of a vector-valued function? Well, if our vector-valued function little r is defined on some open interval around a t-value, which I'll call t0, then the limit as the inputs t approach t0 of the vector-valued function r of t is, first off, let me think of this as the limit as t approaches t0 of the description of r of t. So let me write p of t, q of t, capital R of t. And then how we take that limit is we just do it coordinate by coordinate. So we say that this limit is going to be a vector where the first coordinate is the limit as t approaches t0 of p of t, with similar statements for the y and z coordinates, but using q and capital R. To take the limit of a vector-valued function, we just take the limit of each component. Very simple. You've already seen these kinds of limits in single-variable calculus. I skipped discussing this phrase here. Let me just return to it for a second. I said that our vector-valued function needs to be defined for t values close to t0. So some open interval around t0, we need to be able to let t approach t0. But don't forget, when you take a limit, you're looking for the trend behavior as you approach t0. So your vector-valued function does not even actually have to exist at t0. We're approaching t0, but we're not right at t0. So sometimes students forget that when you take a limit, you're not just plugging in the value t0 or something like that. You're letting the inputs get closer and closer to t0 and trying to see where the function is tending to. We build off of the notion of limit to define continuity. So if our vector-valued function r is defined on an open interval containing t0, meaning that this time we actually care that the function is defined right at t0, and if its component functions p, q, and r are each continuous at t0, where here continuous means continuous in the single variable calculus sense, then the vector-valued function is also continuous at t0, which means that when we take the limit as t approaches t0 of this vector-valued function, we just said above that that's like taking the limit of each component function. But what does continuity of these component functions tell us? It tells us that the limit as we approach t0 of the component function capital P of t is actually going to go to the value p of t0. So that's what continuity means. The value of each component function right at t0 matches the behavior as we approach t0. So in other words, these limits are all just going to be p of t0, q of t0, capital R of t0. In other words, what we're really saying here, if we step back and look at it, is that the limit as we approach t0 of the vector-valued function r of t is just going to be r of t0. That's why students sometimes get confused when they're taking limits and they think that what they're supposed to do is plug in t0. That action of plugging in t naught is really your way of saying that the function is continuous. So you have to be careful because not every function is continuous. But if our vector valued function is continuous, meaning it has nice component functions which are all continuous pieces, then yes, the limit as t approaches t naught of that vector valued function is actually the vector valued function evaluated at t naught. Okay, let's look at an example. We have several questions here for this vector valued function r of t. First, we want to find its domain. Then we want to find the limit, if it exists, at 3, t naught equals 3. Then we want to ask ourselves, is this vector value function actually continuous at 3? So this question here means, is the limit as little r approaches 3 equal to r of 3? And then we'll do the same analysis for limit and continuity for t naught equals 1. Okay, so let's start with the question about domain. So here's our vector valued function. The first component function is natural log of t. The second one is 1 over t squared minus 1. And the third one is 2t. To find the domain of this function, we need to find the domain of each component function and then bring them all together. So what is the domain of the first component function, capital P of t? You can only take the natural log of a positive number, so that's going to be t greater than 0. What about the domain for the middle component function, capital Q? Well, the denominator would be 0 if t were either 1 or negative 1. Every other value of t is possible, so the domain is t not equal to plus minus 1, which we can also write in interval notation as negative infinity through negative 1 through 1, and 1 through infinity. Our third component function, 2t, is just a nice polynomial expression that's defined for all t. So tying these together, we need positive t, but we can't have t equal to 1, and that's it. So the domain of this vector valued function goes from 0 to 1 together with 1 to infinity. Let's now take the limit as t approaches 3. This is going to be the limit of each component function as t approaches 3. Each of those limits exist. So the limit of natural log of t as t approaches 3 is actually natural log of 3. Similarly, the limit of 1 over t squared minus 1 as t approaches 3 is 1/8, and then the last one is 6. The reason I'm able to compute these limits so quickly is because each of these component functions is a continuous function at t equals 3. So these are all familiar functions. We've worked with these functions before in calculus classes. So we know that natural log of t is continuous for any t value greater than 0. Rational functions, which look like polynomials divided by polynomials, that's the kind of function that we have in the middle component here. 1 over t squared minus 1 is similarly continuous when we're in the domain. So since 3 is in the domain of that function, we're continuous at t equals 3. And then the last function is a polynomial that's continuous everywhere. So we want to be able to recognize facts about these basic building block functions because we've already had single variable calculus. So now I can conclude that since each component function is continuous at 3, so is the vector valued function little r of t. The limit that we calculated, natural log of 3, 1/8, 6, this is exactly r of 3. Again, we've worked through limit and continuity now in just a few minutes. These would have been topics that took several weeks in a calculus class, and the reason why we're allowed to do this is because although we're looking at a new type of function, a vector valued function, we're analyzing it just by looking at the component functions, which are not unusual functions. So these are scalar valued functions of a single variable, so you're allowed to use single variable calculus on them. Let me erase this now so that we can answer the final question. So let's repeat finding the limit and analyzing continuity for t naught equals 1. Let's take the limit as t approaches 1. We know that that's equivalent to taking the limit of each component function as t approaches 1. The first component function for the x-coordinate is going to be 0. So natural log of t as t approaches 1 goes to the natural log of 1, which is 0. The third component function being a nice polynomial, we know that that's just going to be 2. However, the middle limit does not exist. We know this because the limit as t approaches 1 from the right is going to be 1 divided by very small positive numbers, so that's going to go to positive infinity. Versus if we approach t from the left, that's going to be 1 divided by very small negative numbers, which goes to negative infinity. Although I wrote equals positive infinity and equals negative infinity as if those were numbers, I want to point out that a limit of infinity does not exist. So the limit as t approaches 1 of r of t does not exist. It doesn't even really matter here that the one-sided behaviors were different. So it's not that it doesn't exist because one side went to infinity and the other side went to negative infinity. It just plain old doesn't exist. Since this limit does not exist, this function cannot be continuous at 1. In fact, 1 is not even in the domain. You can only be continuous at a point in your domain. So this function is not continuous at 1. Now let's move on to differentiation. I'm going to talk through differentiation in a little bit more detail than I did limit and continuity. However, keep in mind the overriding message of this lecture, which is that when we want to discuss differentiation of a vector-valued function, it amounts to differentiation of the component functions. And those are derivatives that you've already learned how to calculate. Okay, so let's dig into differentiation. Let r of t be a vector-valued function defined on an interval containing t0. In fact, let me go ahead and imagine that I'm going to plug t0 into the vector-valued function. Let's say it's this point here, and this is the position vector r of t0. So this curve I've given you on the left is the space curve that the vector-valued function r of t sweeps out in R3. What we want to call the derivative of this vector-valued function at this point can be denoted these two ways. So we have dr dt evaluated at t0, or more simply r prime at t0. It's going to be the limit of a difference quotient, just like for single variable differentiation. So in particular, it's the limit as h approaches 0 of r of t0 plus h minus r of t0 divided by h. This is a difference quotient. It's a change in outputs divided by a change in inputs. In this context, however, the change in outputs is a vector difference. So let's make sense of what this vector difference looks like in the picture to the left. Okay, so I've already imagined that r of t0 is here. Now let's evaluate r on t0 plus h. We're taking the limit as h approaches 0, so normally we would imagine h to be a very small change in inputs, but for the sake of the picture, let me imagine that this is my vector. So this is the position vector r of t0 plus h. This change in outputs here is a vector difference. So it's the second vector minus the first vector. In other words, we can imagine this as the vector that goes from r of t0 to r of t0 plus h. So this is what the numerator is calculating, is this vector that points from r of t0 to r of t0 plus h. And then dividing it by h is really just like multiplying by the scalar 1 over h. So this difference quotient is a scaled version of this vector I just drew. Now if this limit exists, then as you can see, r prime of t0 would be a vector. And in fact, as we let h go to 0 and you imagine how this vector would change, we're going to think of this as the tangent vector. So it's tangent to the graph of r of t at the point t0. We'll also call this a velocity vector, particularly a little later when we talk about motion. Now, how would you compute this difference quotient? Well, when you do vector subtraction, you do it component-wise. So it's x component minus x component, y component minus y component, z minus z, and then dividing by scalar is the same thing. It goes to each component. So if you actually wrote out this difference quotient, then the limit of this difference quotient is actually going to return you back p prime, q prime, r prime. And this is typically how we will compute derivatives in this class. So you've already gone through differentiation of scalar valued functions of a single variable in single calculus. So if we have a vector valued function with 3 component functions and we want to differentiate it, then when we can, we just want to differentiate each component function in the usual way that you're familiar with. While we're talking about differentiation, let me throw in a definition here. Imagine that you started with the curve. So perhaps you started with this curve and you were able to write down a vector valued function which gave you that curve. That's actually called parametrizing the curve. And if I write down a nice parametrization which is differentiable and which never has a 0 tangent vector, then we say the curve is smooth. So a smooth curve is one that has a nice differentiable parametrization where the velocity vector is never 0. Okay, I did kind of a lot on this slide because I think it's important to understand what differentiation is. But again, the main message here is that to differentiate little r of t, we're going to differentiate p, q, and capital R, and those are just going to be regular single variable functions. We're going to differentiate a lot in this unit actually, so let's go over some properties of differentiation that we will want to use. These will probably not surprise you because most of them are going to remind you of properties of differentiation that you've already seen. Okay, so I have a hypothesis up here, but we're just going to talk through these properties one at a time. If I want to differentiate a vector valued function, which is actually a constant function, so imagine here this vector k is just the constant vector 1, 5, negative 2, then its derivative is 0. Shouldn't be too surprising. Another unsurprising result is if I have a vector valued function little r of t and I scale it by some number c, so c here is just a constant like 5, then the derivative of c times r of t is just c times r prime. Another result which you can probably expect is the derivative of f plus g is f prime plus g prime, and similarly the derivative of f minus g would be f prime minus g prime. The fourth property here is a product rule, except it doesn't make sense to take a product of 2 vectors, right? We never have 2 vectors just multiplied together. That's not an operation. So here h of t is a scalar and r of t is a vector valued function. You could imagine this kind of like, I'll just give you an example. T squared times the vector cosine of t, sine of t, t cubed. So little h of t is like the t squared out here. It's a scalar in front of the vector, but it itself is a function of t in its own right. So we have some scalar function of t times a vector valued function of t. The derivative of this product, scalar function times a vector function, follows the familiar product rule that you've seen before. So that's going to be little h prime times r plus h times r prime. Okay, these 4 properties all look exactly like properties of differentiation you've seen before. Let's go on to some properties which might look a little bit new because we have some new operations in multivariable calculus. So I said there's no such thing as a vector times a vector, just familiar multiplication, but we do have dot and cross product, and we can differentiate quantities like f dot g and f cross g. And in both cases, they also follow the product rule. So the derivative of f dot g is f prime dot g plus f dot g prime. And similarly, the derivative of f cross g is f prime cross g plus f cross g prime. Be careful here to watch out for your order because cross product is not commutative, so make sure you don't do g cross f prime because that would actually not be correct. And in this final property, we have a chain rule statement here. G of t is a scalar valued function, and capital F is a vector valued function. So our outside function is just f of t, that's just a regular vector valued function, but then let's say we're plugging in something like t cubed. if we want to differentiate this composition, then it's going to follow the familiar chain rule. Derivative of the outside evaluated on the inside times derivative of the inside. So we can write that as f prime of g of t times g prime of t. I would actually, in practice, typically write this as g prime of t times f prime at g of t, because g prime of t is actually a scalar and f prime is a vector. And to me, that just seems like the more natural order of a scalar times a vector. We'll do integration real quick. It's just going to be this slide. And by now you probably expect what the result is. If I want to integrate this vector-valued function from 0 to 1, what I'm going to do is just integrate each component function from 0 to 1. So that's just going to be 3 one-dimensional integrals. Let me go ahead and do that. So the integral from t equals 0 to t equals 1 of f of t dt is going to be component by component integration. So we're going to get the integral from 0 to 1 of sine, the integral from 0 to 1 of t squared plus t dt, and the integral from 0 to 1 of 1 over 1 plus t squared dt. Okay, you should know how to do these. I threw in the third one just to see if you would remember that antiderivative. For the first one, it's what? Negative cosine. And then we're going to evaluate it from 0 to 1. Let's see, that's actually just the first component. And then from power rule, we get 1/3 t cubed plus 1/2 t squared. The third one, that's an antiderivative you might have forgotten, or perhaps you've never seen it before, but the antiderivative of this one particular function is arctan of t. Okay, and this is a definite integral, so now we just plug in our top bounds, subtract off the bottom bounds. This is just component by component regular integration. We can simplify this a little bit. So cosine of 0 is 1. Let me write this as 1 minus cosine of 1. 1/3 plus 1/2, if you like, that's 5/6. And then what is the arctan of 1? That's the angle whose tangent is 1 between negative pi over 2 and pi over 2. So that's actually pi over 4. And then arctan of 0 is 0. Okay, so for this definite integral, we just did 3 definite integrals of each component. You can probably anticipate the final statement in this lecture, which is that if the derivative of capital G is capital F, where both of these are vector-valued functions, then we call capital G an antiderivative of capital F. So very similar to integration as you've seen before. Okay, so this was a quick crash course in limits, continuity, differentiation, integration. Again, major topics that feel like they should take a lot of time in a regular calculus course, but here, because it's really just notions that you've seen before done to each component function, we do it in just one lecture. Thank you for your attention.